Let's revise 10th standard ICSE Physics Chapter 2. Now in section B, let's study the different forms of energy. Mechanical energy is of two types, potential energy and kinetic energy. Potential energy is the energy possessed by an object by virtue of its configuration or position. It is of two types, gravitational potential energy and elastic potential energy. Gravitational potential energy is because of its position, because of its height, and elastic potential energy is because of its shape, the configuration. Now gravitational potential energy is calculated as mgh, and we have studied this derivation in section A. Remember, the work done when you lift an object is negative by gravity. So the potential energy is considered to be a negative energy. So when you calculate the potential energy near the Earth's surface, let's suppose it is minus 40 joule. Now when we do numericals, we will ignore this negative sign. But let's understand what happens as the object goes far away from the Earth. Now in numericals, we assume that the value of g is constant. But as you go far away from Earth, the value of g in space decreases dramatically. So the magnitude of the potential energy decreases. Let's say it's 20. However, minus 20 is a bigger number than minus 40. So theoretically, we say that the potential energy is increasing. This is happening because potential energy is a negative energy. What this means is, at infinity, the potential energy becomes 0 joule. However, we don't have such numericals. We will have numericals pertaining to near the Earth's surface. So we will just use this formula and we will not use a negative sign for potential energy while calculating. Elastic potential energy is because of the elasticity of an object. For example, when you compress a spring or expand it, on releasing it, it may come back to its original shape or original configuration. That is true even for rubber band and many other objects. So when you compress a spring, some energy is stored in it. That is the elastic potential energy. Next, kinetic energy. That is the mechanical energy in an object by virtue of its motion. And its formula is half into mass into square of velocity. Now potential energy always has to be converted first into kinetic energy by any object. Then only that kinetic energy can be converted into other forms like electrical energy, sound energy, heat energy, etc. Potential energy cannot be directly converted to any other form of energy except kinetic energy. Now let's derive this equation. Imagine there is a car moving with mass m at a certain velocity. Brakes are applied to slow it down and stop it. So let's understand how much energy was required to stop the car, which would be equal to the amount of kinetic energy that the car possessed before the brakes were applied. So we know that the work done in stopping the car is F into S. The displacement is in the direction of force here. Now force is mass into acceleration. So that can be substituted. But what about displacement? Well, let's use the laws of motion, the equations. One of them is v square is equal to u square plus 2as. But here the acceleration is negative, it's retardation since the brakes are applied. So it should be v square is equal to u square minus 2as. This goes here. And the final velocity, by the way, was 0 because the car came to a stop. So this becomes 2as is equal to u squared. S is equal to u squared upon 2a. So substituting this value for s and this value of f out here, we get f is equal to ma into u squared upon 2a is equal to half mu squared. And the work done by the brakes in stopping the car is equal to the kinetic energy of the vehicle. So we can say kinetic energy is equal to half mu squared. Generally, we denote velocity as v. So the general formula is half mv squared, where v is the velocity at which the object was moving. Next, let's derive one more formula. Now, if you look at the formula of kinetic energy, you will notice that if the mass is doubled, the kinetic energy will also be doubled. But if the velocity is doubled, then the kinetic energy will be quadrupled because of the square here. Now let's find out the relationship between linear momentum and kinetic energy. Momentum is a product of mass and velocity both. You see, when an object is moving, how much force it would apply or how much force is required to stop it depends on two factors, its mass as well as its velocity. So momentum takes into consideration both these quantities. Now, velocity is momentum upon mass. If we substitute this value in this equation and we solve further, m and 1m got cancelled. So finally we got this. Cross multiply, the equation is momentum square is equal to 2 into mass into kinetic energy. Now there are two more ways to write the same thing. Square becomes square root, or you cross multiply and you get this. Now this helps us to understand a few things. For example, if there are two objects, one is light in mass and one is heavy. So if both the objects have the same momentum, then the lighter mass will have greater kinetic energy. Then only the momentum will be same. On the other hand, if the two objects have the same kinetic energy, then the lighter mass will have lesser momentum. So with the help of these equations, you can find out that if two objects have different mass and same momentum, then which one will have more or less kinetic energy, and vice versa. Next, let's talk about a theorem called work energy theorem. Let's take an example. If there is a car moving with certain velocity u, it has mass m, a force, an acceleration force is applied on it. So its velocity will increase. Let's say the final velocity is v. Yes, in any theorem we need to state all these variables first. And the displacement produced is s. So if the engine provided an energy of 400 joule, then the increase in its kinetic energy will also be 400 joule. This seems fairly straightforward and logical. Here we are assuming that none of the energy is getting wasted as heat energy, which is not possible because there will be friction between the tires of the car and the road. So initially the car had some kinetic energy. After accelerating, it will have a greater kinetic energy, and this increase in kinetic energy is equal to the work done by the engine on the car. Let's prove this mathematically. So the work done is F into S. Now let's use this equation of motion. So u square comes here. I want S alone, so that I can substitute this value here. And F is of course m into a. Here there is no retardation, there is acceleration. Substitute this value here. So after the substitution, I cancel a and I get this. Open the bracket and let the denominator be separated. So I get half mv squared minus half mu squared. This means the work done is equal to the final kinetic energy minus the initial kinetic energy. This is the work energy theorem. Now let's talk about the different forms of kinetic energy. First, translational kinetic energy, which is the energy possessed by an object moving in a straight line. For example, a monoatomic molecule, a single atom, always has translational kinetic energy. Next, we have rotational kinetic energy. That is because an object is rotating. For example, the wheels of a car. Some objects may have both translational as well as rotational kinetic energy. For example, the wheels of the car are not just rotating, they are also moving forward. So they have both the types of energy. Even a diatomic molecule will have both the forms of energy. And the third type of kinetic energy is vibrational kinetic energy. For example, the string of a guitar. Even the polyatomic molecules have three kinds of energies: vibrational, rotational, as well as translational. Next, let's talk about the conversion of potential energy into kinetic energy. As you can see in this diagram, the spring was compressed and a ball was kept on it. So this spring has potential energy, elastic potential energy. But when we release the spring, the potential energy is converted into kinetic energy, and this kinetic energy is transferred to the ball, and so the ball also possesses kinetic energy now and it moves. A similar phenomenon happens when you shoot an arrow with a bow. Apart from potential energy and kinetic energy, we have other forms of energy as well. So let's study about that. Solar energy. Well, that is the energy possessed by the sun. And that is the energy we get through the radiations from the sun. This solar energy is very useful. It can be converted into electrical energy in two ways: a solar furnace or a solar cell. A solar furnace focuses all the solar radiations onto a black container, because black absorbs all the sun's rays, in which there is water. concave mirrors can be used to focus the sun's rays. The temperature of water will increase a lot, and after such a tremendous increase, it will boil, it will form steam. And whenever steam passes through a pipe with great force, and it is used to rotate the turbines, which is like a wheel, and when the turbine rotates, electrical energy is produced. The mechanical energy gets converted into electrical energy. You see, the turbine is connected to a generator, and inside the generator we have a coil wire made up of copper, which rotates in a magnetic field. And whenever a metallic wire rotates in a magnetic field, electricity is produced. That is because of a phenomenon called change in magnetic flux, but that you will study in chapter number 10, electromagnetism. So here, all you need to know is, whenever a turbine rotates because of wind, water, steam, it is connected to a generator and electricity is produced. Another way of converting solar energy into electrical energy is by using a solar cell. Now, in a solar cell, the light rays fall on certain chips of silicon, germanium, etc., which directly produce electricity because of the solar radiation. These semiconductors are used to make solar cells, and together many solar cells can form a solar panel. You may have seen many solar panels on terraces of buildings, especially hospitals or movie halls. They're also found on top of street lights. It's non-polluting, and in the long run, it saves a lot of electricity bills. The next form of energy is hydro energy. That is the energy of fast-moving water. So when we build dams across rivers, we are using the hydro energy to produce electricity. When dams are built, the water has a lot of potential energy, and then when the valves are opened, the water falls on the turbine with great force, and whenever the turbine rotates, electricity is produced. The next form of energy is electrical energy, by far the most versatile form of energy, because electrical energy, once produced, can be converted to any form: light, heat, kinetic, etc. Then we have something called nuclear energy. Nuclear energy is the energy released by the nucleus of atoms, and this can be obtained by two processes: nuclear fusion and nuclear fission. In nuclear fusion, which happens in all the stars including the sun, smaller atoms like hydrogen, they combine to form heavier elements like helium, lithium, and so on. This is not a chemical reaction. Electrons are not involved here. The nuclei fuse together, and the product formed has slightly less mass than the reactants. This difference in mass is converted into energy. According to Einstein's equation, E is equal to mc squared, mass can be converted into energy. Again, you will study this in detail in chapter 12, Modern Physics and Radioactivity. Another nuclear phenomenon is nuclear fission, which is used on Earth by us to produce electricity or in atom bombs. In nuclear fission, a heavier nucleus of an atom like uranium splits into smaller nuclei like krypton and barium. And again, in this process, some mass is converted into energy. And this conversion the conversion produces tremendous amount of energy. An atom bomb has so much energy, it can destroy a small town. So this energy can be used constructively as well. In nuclear reactors, the nuclear fission produces energy which is used to boil water. Steam is produced. Steam will rotate the turbine, and electricity is produced. The next form of energy is geothermal energy. This is the energy present inside the Earth's crust, in the interior of the Earth. And what produces this energy are the nuclear disintegrations in the mantle and the core of the Earth. That is why magma is so hot. But again, this geothermal energy is useful. We can use it. Hot springs are created because of the geothermal energy. Water, which gets accumulated underground, if they come into contact with hot rocks because of the geothermal energy, then the water becomes steam and comes out with great force. Now this steam has a lot of energy which can be used either to warm houses in cold countries like Iceland, or it can be used to move turbines and produce electrical energy. The next type of energy is wind energy. It is used to run windmills. When the blades of the windmills rotate, again the turbine rotates and the generator coil rotates and electricity is produced. Wind energy is also used in windmills to make flour out of grains. The next form of energy is sound energy. Any vibrating object produces sound energy which can be perceived by our ears. In a microphone, the sound energy is converted into electrical energy, and in a speaker, a loudspeaker, this electrical energy is again converted into sound energy. The next form of energy is magnetic energy, which is possessed by magnets. Opposite poles attract each other. Magnetic energy is very important to produce electricity. The generator works on the principle of magnetic fields. And finally, mechanical energy, which is of two types, potential energy and kinetic energy. Now, we should be aware of some examples of transformation of energy. Mechanical energy to electrical energy, the best example would be a generator or a dynamo, where the mechanical energy of rotation of the turbine is converted into electrical energy. Next example is electrical energy to mechanical energy, the opposite, which is done by motor, like the motor in the fan. It converts the electrical energy into mechanical energy, which is kinetic energy, of course. Even in a mixer grinder or in cars. Next, electrical energy to heat energy, that's straightforward, electric iron. Heat energy to electrical energy. We have certain devices like the thermocouple. The thermocouple is useful in converting heat energy into electrical energy. Don't confuse this with a solar cell. A solar cell converts solar energy into electrical energy. The next topic is electrical energy to sound energy. I'll just give an example of loudspeaker. And sound energy to electrical energy is the microphone. Electrical energy to chemical energy. Well, when you charge a battery, the electrical energy is getting converted into chemical energy inside the battery, and it is stored as chemical energy. And when you use the battery again, this stored chemical energy is once again converted into electrical energy, which is used for the working of the mobile phone or the appliance. So the reactions inside the electrolyte of a battery is reversible for charging and discharging. Next, chemical energy to light energy. Well, when you burn fuel, fuel has chemical energy stored in it. During photosynthesis, food was prepared, so the solar energy was trapped in it as chemical energy, and when it is burnt, that chemical energy is converted into light energy and even heat energy. What about light energy to chemical energy? This can also happen in photosynthesis, like I just explained. And there are certain photochemical reactions which take place, for example with silver salts, where light energy can produce a chemical change. The next topic is electrical energy to light energy, which happens in bulbs. Light energy to electrical energy is in solar cells. Heat energy to mechanical energy, for example steam engine, where the heat is used to convert water to steam, and this steam moves the engine. That's mechanical energy. Chemical energy to heat energy is the same fuels, burning of fuels. When you burn a firecracker, the chemical energy inside it is converted into light energy, sound energy, heat energy, and even mechanical energy, because the parts of the firecracker may just fall apart in different places. Chemical energy to mechanical energy. For example, in a vehicle, where the chemical energy of the fuel of petrol is finally converted into the mechanical energy of the vehicle. But doesn't happen directly. First, the chemical energy is converted into heat energy, and the heat energy moves the machine parts. Electrical energy to magnetic energy. This happens in an electromagnet. Even metals like copper or aluminium can be converted into a magnet by passing electricity through a wire wound around it. This is called an electromagnet. Of course, as soon as you switch off the electricity, it would no longer be a magnet. It's temporary. Nuclear energy to electrical energy takes place in nuclear power plants, which I just explained. And finally, mechanical energy to heat energy. Now, it's interesting to note that whenever a water falls from height in a waterfall, the temperature of the water at the bottom is slightly more than the temperature at the great height. This is because at the great height it had potential energy. When it falls down, that potential energy of water is converted into kinetic energy, and when the water smashes against the rocks on the bed, the rock bed, some of the kinetic energy is converted into sound energy and some of it is converted into heat energy. So it heats up the water a little bit, and hence the temperature is slightly more. Now, one thing we need to keep in mind is that whenever there is conversion of energy, it's not 100%. There is always a wastage of energy, a degradation of energy. For example, when you switch on the light, the 100 joule of electrical energy won't be converted into 100 joule of light energy. Perhaps the efficiency is just 60%. The remaining 40% will be wasted mostly as heat energy, which is dissipated into the environment and the atmosphere.
10th Standard Physics, Chapter 2, Part B, Different Forms of Energy. Mechanical energy has two forms, potential and kinetic. Potential energy can only be converted to kinetic energy, after which the kinetic energy can be converted to any other kind of energy like electrical, magnetic, heat, sound, etc. So kinetic energy is very versatile. The total potential and kinetic energy of a body is called mechanical energy, which is always a constant unless there is some wastage of energy. Potential energy is defined as the energy due to its position or size and shape, which is also called configuration. It is denoted by U. It is of two types. First of all, gravitational potential energy because of the height of an object above the earth, and it's because of the gravitational attraction of the earth. Note that the gravitational potential energy of a body is always zero when it is at infinity, because the force of attraction there is zero. I have been at infinity and checked the force of attraction of Earth, and it is indeed zero over there. You can check it too. Cancel this sentence. Now, gravitational potential energy is always considered as negative. This paragraph, mark it as read, it won't be tested. Elastic potential energy. This is the potential energy due to the stretching or compressing of an object, a non-rigid object. For example, when you stretch a rubber band or a spring or the bowstring, you are storing the energy in it as elastic potential energy. This is the definition. For gravitational potential energy, we have a formula, mgh, which is the same as the work done in raising an object to a particular height, which we studied in the previous section. But note that in numericals, when we calculate the potential energy, we are actually calculating the increase in potential energy because we assume the potential energy on the ground to be zero. The truth is that even on the ground, the potential energy of an object is not zero. It would be zero only when the object is at the center of the earth. Now, if you want to find the difference in potential energy, this is the formula. Kinetic energy is the energy due to its state of motion. Anything which moves has kinetic energy. And it has a formula, half into mv squared. There is a derivation for it. First of all, we know that the work done by an object is force into displacement. Now, imagine there is an object moving with a particular velocity. It has some kinetic energy. It is doing some work, which is equal to force into displacement. In order to stop it, we will apply some force, like the brakes of a car. The amount of work done in stopping that object will be equal to the kinetic energy it possesses. So now we can say that the kinetic energy is equal to the force that we applied, the force of retardation, into the displacement. It won't come to a stop immediately. It will travel some distance and then come to a stop. So kinetic energy is F into S. Now F is ma, mass into acceleration. Substitute that. Similarly, to substitute displacement, let's work out something. Now we know that there is a kinematic equation saying v square is equal to u squared plus 2as. In this particular case, when we applied the brakes, the final velocity was 0. The initial velocity, we take a general symbol as v. We could have kept it as u as well. Since it is a deceleration, we put a minus sign. 2as goes on the other side, and then we cross multiply to get s is equal to v squared upon 2a. So substitute that for the value of s. So after substituting the values of f and s, we are left with this. A and a gets cancelled, and that's how we get half mv squared or half mu squared. But notice here v is not the final velocity, it's just the initial velocity. We've generalized it with v. So that's the derivation of the formula of kinetic energy. Now we know that the formula of momentum, linear momentum, is mass into velocity. So we have yet another relationship between kinetic energy and momentum. Well, v is equal to p upon m. M goes down. So if I substitute this v with p upon m, and on solving, p square upon m square, mm cancelled, I am left with a new formula, k is equal to p square upon 2m. Cross multiply, I get P square is equal to 2mk, or P is equal to square root of 2mk. So that's the relationship between momentum and kinetic energy. What I notice here is that P square is a numerator and mass is a denominator. So I can say that the kinetic energy is directly proportional to the momentum or square of momentum, but it is inversely proportional to the mass of the object. So if momentum is constant, I can simply say kinetic energy is inversely proportional to mass. That means lighter the mass, more is the kinetic energy. Notice this is true only if momentum is constant. The logic behind this fact that the greater the mass, less is the kinetic energy is because if momentum is constant, then the object having greater mass, that is body B, will have lesser velocity, because momentum is constant and momentum is mass into velocity. So again, if A is lighter than B, then A will have more kinetic energy than B, because mass of A is less than the mass of B. And by the way, velocity of A will be greater than the velocity of B, because momentum is equal. Simply speaking, kinetic energy is inversely proportional to mass when momentum is constant. What if kinetic energy is constant? Then the momentum squared is directly proportional to mass. That means the lighter the body, less the momentum. So this relationship is true only when kinetic energy is constant. So out of object A and B, who will have a greater momentum? B, because its mass is heavier. So you don't have to worry about this calculation. You just have to remember this. This is true when kinetic energy, when momentum is constant, and this is true when kinetic energy is constant. So what kind of question will be asked? That body A has less mass, body B has more mass, kinetic energy is equal, who has a greater momentum? We just have to say body B. That's it. We don't have to calculate anything. And how can we remember which one is greater? By remembering these two expressions. So this calculation is not important. Now the work energy theorem. This is important. This can come in exam for derivation. First of all, the statement. When there is an increase in kinetic energy of a moving body, that increase is equal to the work done by a force acting in the direction of the moving body. For example, if a car is moving with some initial velocity and it has a kinetic energy, let's say 2000 joule. After some time applying the accelerator, its velocity increases, so the kinetic energy also increases to 3000 joule. So the increase in kinetic energy is 1000 joule. That increase is equal to the work done by the engine force. So the engine applied a force on the car and the work done by the engine is 1000 joule. That is why the kinetic energy increased to 1000 joule. Here we are assuming that no energy is being wasted due to friction. That's an assumption. So whenever we derive something, always introduce all the variables. This derivation is similar to the one on the previous page. We start with the fact that work done by the force, in this case the engine, is equal to force into displacement. We will substitute F, we will substitute S, and we will get what is asked. F is of course mass into acceleration here. Now S, we start with the kinematic equation V square is equal to U square plus 2AS, but note that here V is not 0. So we simply rearrange the terms and get S alone, which is V square minus U square upon 2A. Substitute that value here, AA gets cancelled, and we are left with half M V square minus U square, open the brackets, we get this. Now half mv square is the final kinetic energy, half mu square is the initial kinetic energy. So we have proved that the work done by the engine is the difference in the kinetic energy, and that is the work energy theorem. Proved. The forms of kinetic energy. Translational kinetic energy is because of motion in a straight line. Example, a car moving in a straight line. Rotational kinetic energy is because of rotation. Example is spinning top, etc. Even the atoms of a diatomic or polyatomic molecules have rotational kinetic energy. By the way, molecules of monoatomic gases like neon, they have only translational kinetic energy. They will not rotate. Vibrational kinetic energy is due to vibration about a main position. For example, the string of a guitar which is plucked. Don't just write string of a guitar. Complete answer would be which is plucked. Even the polyatomic molecules will have vibrational kinetic energy. The blue sentence is cancelled. Objects may have multiple forms of energy also. For example, a rolling ball and a wheel have both kinetic energies, translational and rotational. Polyatomic molecules have all three types of kinetic energies. Now, the difference between potential energy and kinetic energy. The definitions: potential energy is equal to the work done in bringing the body to its changed state, and kinetic energy is equal to the work done that a moving body can do, in fact, before coming to rest. It can change only to kinetic energy. It is more versatile. It can change to any other form of energy, including potential energy. It does not depend on the speed of the body, but it does. Now, there are many examples of conversion of kinetic energy into potential energy and vice versa. For example, when you raise a hammer at a height, you have stored potential energy in it, and when it comes down on a nail, that potential energy is converted into kinetic energy, which is useful in driving the nail into the wooden piece. Secondly, when you wind up a watch spring, it has elastic potential energy, which is used for it to work and the hands of the watch to move. That is again potential energy converted into kinetic energy. Similarly, when the string of a bow is pulled, it has potential energy, which can be converted to kinetic energy, which is transferred to the arrow, and then the arrow has a kinetic energy and it flies. A compressed spring also has potential energy. When you release it, it gets converted to kinetic energy, and then that gets transferred to the ball, and the ball flies. Next, the different forms of energy. Solar energy, that's the energy radiated out by the sun. Solar energy can be used in the following ways: solar furnaces and solar cells, cancel solar panels. A solar furnace has a large parabolic mirror, that is a curved mirror, a concave mirror, which will focus all the sun rays onto a small area. And in that small area, a black box is kept because black absorbs all the heat. Inside it, we can have water, which will boil to produce steam, and the steam can be used to run a generator and produce electricity. Solar cells are made up of substances like silicon, germanium. They directly convert the solar energy into electrical energy. Many solar cells together are called solar panels. Next type of energy is heat energy. Well, it is released when you burn something, especially fossil fuels, and the heat can be used to produce steam, and steam can be used to run a generator to produce electricity. Light energy is again a form of energy in the presence of which we see things. Our main source of light is the sun. Chemical energy is the energy stored in fuels, such as in coal, petroleum, natural gas. So when we burn it, this chemical energy can be converted to heat and light energy. But how did the chemical energy get stored in the fuels in the first place? Well, it all starts with photosynthesis, which plants do in the presence of sunlight. When these plants and animals which feed on plants die, some of them gets fossilized over millions of years, gets converted to fossil fuels. So indirectly, the energy which we get from fossil fuels is obtained from the sun. Hydro energy is the energy possessed by fast moving water. So when we build dams across rivers, the water has potential energy behind the walls of the dams, and when we open the channels and the water flows on a turbine, the turbine rotates, and that's when electricity can be produced in the generator. And electrical energy is again a very useful and versatile form of energy because it can be converted to any other form of energy. In an electric cell, the chemical reactions are used to convert the chemical energy into electrical energy. So that's the source of electrical energy. Nuclear energy, the energy released due to the loss in mass during the process of nuclear fission and fusion, is called nuclear energy. For example, if I have a uranium atom, it's radioactively unstable. It may split into two or more parts, like lighter elements and some neutrons. This is called nuclear fission, where the total mass of all the products is slightly less than the total mass of the uranium atom. Where did the mass go? Well, as per Einstein's mass-energy relationship, E is equal to mc squared, some of the mass can be converted into energy. That's nuclear energy. The opposite is also possible. If we have smaller atoms like hydrogen, and they fuse together to form a bigger nucleus like helium, again the mass of the product helium is slightly less than the total mass of the reactants, that is the hydrogen atoms, because the loss in mass was converted into energy. This energy can be used for constructive purposes as well as destructive purposes, like in a nuclear bomb. Constructive purposes would be in a nuclear power plant, where it can be used to heat water into steam, and steam runs the turbine, and a generator works and electricity is produced. Next, we have geothermal energy. That's the energy released due to the nuclear disintegration in the interior of the Earth. So this is the reason why we have hot springs and geysers. The heat inside the Earth boils the water which comes out forcefully. That's geothermal energy, which is useful as it can be used to run some turbines to produce electricity. It can also be used to heat houses in cold areas. Wind energy is possessed by wind. It's kinetic energy. If we have windmills, then the wind energy can turn the turbines and produce electricity. Sound energy is caused by the vibration of any object. It's a type of mechanical energy, and when we hear it, it's because of the ear membranes in our ears vibrating. Magnetic energy is possessed by a magnet, due to which it can attract ion filings, etc. For example, electromagnet has magnetic energy. Mechanical energy is the total potential and kinetic energy. Now the conversions. Mechanical energy to electrical energy is done by dynamo or generator, whereas electrical energy to mechanical energy is by a motor, which is there in all moving machines like a fan, a mixer grinder, a washing machine. Electrical energy to heat energy, for example, electric iron or water heater, and heat energy to electrical energy by a thermocouple. It's a device. Due to the difference in heat energy, electricity flows. Electrical energy to sound energy is by a loudspeaker, and the reverse is done by microphone. Whatever you speak is converted to electric signals. When you charge a battery, you are converting the electrical energy from the socket, from the power supply, into chemical energy stored in the battery. And when you use the cell or the battery, you are again converting that chemical energy into electrical energy. When you light a candle or any fossil fuel or burn anything, chemical energy is converted to light energy, and even heat, of course. And in photosynthesis, light energy is converted to chemical energy and stored in it as food. An electric bulb converts electrical energy to light energy, and a photocell, like a solar cell, converts light energy into electrical energy. Electrical energy can also be converted into magnetic energy using an electromagnet. So you need to remember all these examples that we've just studied. Chemical energy to mechanical energy. Well, it doesn't happen directly. First of all, in automobiles, petrol or diesel is burnt, so chemical energy is converted to heat energy, and that heat energy is converted to mechanical energy, more specifically kinetic energy. Nuclear energy can be converted to electrical energy with the help of nuclear reactors, with the process of nuclear fission. Nuclear fusion cannot yet be used on Earth. It's just too difficult to maintain it. Mechanical energy to heat energy, mark it as a GR. When the water falls from a height, it has initially potential energy, which is converted to kinetic energy. That's mechanical energy. When it strikes the bottom, the rocks at the bottom, we hear a loud sound of the waterfall, and a part of the kinetic energy is converted to heat energy. That's why the temperature of the water rises at the bottom of the waterfall. Similarly, the moving parts of a machine get heated because of friction. Again, mechanical energy is converted to heat energy. Now, not all the form of energy can be converted into a useful form. Some of it is wasted. That is called degraded energy or degradation of energy or dissipation of energy. And that's mostly because of friction. We can't avoid loss due to heat energy. Every machine produces heat. Even an air conditioner does. No machine is 100% efficient. Example, a bulb or a vehicle.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.